Welcome everyone. A very important video. This video is about 555 timer, as the title of the video suggests. And you are a electronic engineer, electrical, or be an engineering student, or anyone who is trying to work with timing, delays, triggering a signal at a certain time or moment, or dealing with clock frequency. This is going to be extremely important video, and what I'm going to show you here is using 555 timer. How do you set a delay? So for example, in this video, in this project, what we are doing is using the 555 timer. In this configuration, these are not just random values for the resistors. There is a math behind it. How do we choose the value of these resistors and capacitors such that in this configuration they generate a trigger moment every 1 second, or you want to call it a delay. Every 1 second the output of the 555 timer goes high and then goes off. Every 1 second it generates a pulse. This pulse is fed into a 4-bit ripple binary counter, which when this trigger moment is fed into the binary counter, that's when it starts counting up. It starts with 0 and then goes to increments by 1 every 1 second. It happens every 1 second because the 555 timer has a 1 second trigger moment. So every 1 second logic goes high. When logic goes high, clock frequency is high, which basically means the counter is going to go up by 1. So in LEDs basically are connected to the output of the binary counter, which basically reflects the binary code, and then we fed these outputs of the binary counter into 7-segment decoder so that we can connect it to a 7-segment, and then we can see the output here in decimal as well. Note that there's only 1 7-segment, so it's only going to display from 0 to 9, but 9 to 15 is going to be displayed over here. So this is what the goal is to achieve, is to have a 1 second 4-bit digital counter with a display. So there are a bunch of components in there. In last video we covered 7-segment decoder, how we can hook them up on this part, but something very new and very important over here. So before I get started, I want to show you something, and I'll leave the link of these are some random websites, and I was able to get information about 555 timer. So 555 timer is a 8-pin chip. It comes in a dual inline package. So if you see at the top, there's a notch right here, correct? So that means to the top left, this is ground, trigger, output, reset. Pin number 5 is control voltage. 6, 7, 8 is usually the power supply. Right? So pin number 1 is just simply the ground, connected to the ground. Pin number 2, let's see what pin number 2 is doing. It's the trigger pin, okay? It works just like a trigger moment or a starter pistol to start the 555 timer run. And know that it's an active load. That means it needs to be 0. Once it's 0 or 1/3 of the supplied voltage, only then the triggered this pin will be triggered. Okay, 1/3. It has to be below 1/3 of the supplied voltage. Supply voltage is going to be anywhere between 4.5 to can go up to 12 volts. In this example, we are keeping it 6 volts. Pin number 3 is the output pin. Pin number 3 here is the output pin. It's only going to generate a 0 volt or whatever the power supply value is. So if it's 6 volts, then it's going to either generate 0 volt or 6 volts. Pin number 4 is the reset. Reset is also active low, just like the trigger input. This needs to be connected to the supply voltage of the 555 timer to operate. So pretty simple. You're just gonna supply whatever the supply voltage here and short it to the pin number 4. Pin number 5 is the control voltage. In this example, we are simply not gonna use it, In many circuits, you just simply disconnected the ground, or you connected even when connected through a ground, it is usually done through a small capacitor, but we just not gonna use that pin. Pin number 6 is, the purpose of this pin is to monitor the voltage across the capacitor that is discharged by pin number 7. Okay, when this voltage reaches 2/3 of the supply voltage, that is the timing cycle ends and the output on pin 3 goes low. So pin number 6 and 7, threshold and discharge, essentially these basically helps us to set a certain timing interval, and I'm going to show you a little I'm going to explain that a little bit more in the next few minutes. Let's look at discharge. This pin is used to discharge an external capacitor that works in conjunction with a resistor to control the timing interval. Pin number 7 is connected to supply voltage through a resistor and to ground through a capacitor. And finally, pin number 8 is just simply a power supply, and like I mentioned, it needs to be at least 4.5 volts and no greater than 15 volts. So that's the pin configuration of the 555 timer. I also want to go through one article. It's actually on allaboutcircuits.com, and I'll leave the link in the description as well. So 555 timer, when configured in this fashion, can be used to create a certain clock frequency or set some kind of a timing delay. That's what the 555 timer is, basically setting up a timer. It's a timer chip. So these R1, R2, R2 and C, these three parameters, these three passive components, they basically decide how much is going to be the timing delay. Now in this example, we want to set the clock frequency of 1 Hertz, which is basically equivalent to 1 second. So if you look at over here, the good thing about this article is you don't have to do the math, which is basically, if you need to, and as an engineer you should be able to do that. Okay, time is a reciprocal of 1 over f. So here's an equation right here, 0.7, roughly 0.7 times R1 plus 2R2 times C. Remember, R1 is this, R2 is this, C is this. So our goal is to have this value of 1 second. If you want the timing period to be 1 second, then what should be the value of R1? What should be the value of R2? What should be the value of capacitors right here? So you have to plug in some numbers and do the math such that t equals to 1, correct? Now here is a online calculator that will save you a lot of time. So I just went in there. So I chose, if the capacitor value is going to be 10 microfarad and the resistance R1, R2 are going to be 40 and 52 kilo ohms. If I hit calculate here, it tells me the time period is gonna be 999 milliseconds, almost equivalent to 1 second, frequency of 1 Hertz. And reciprocal of frequency is basically gonna give you time period. Duty cycle. What does duty cycle means? What does mark space ratio means? What does time high and time low means? Okay, let's look at it. Remember, what's going to happen every 1 second, it's going to trigger a signal, which is going to be anywhere between 0 to whatever the power supply is, right? So time period is basically the positive part and the negative part of the cycle right here, correct? If you notice here, positive part is more and the negative part is more. So the duty cycle here for the positive half wave is more compared to that of the negative half, correct? So that is the time period, the amount of time it takes to complete one signal. One complete signal is basically the positive half and the negative half, correct? Now if you look at the time high, what is time high? It's basically when the amplitude is that of a supplied voltage. So it's high over here and then it's low over here. So low is the basically time low and time high. For how long it's high, for how long it's low in terms of the time. That's what the duty cycle is. And mark space ratio is just a ratio of the high time and the low time. It's not too significant at this point, and also you might not hear too much about it, but duty cycle is extremely important, and it's usually presented in percentage. Okay, so if you have, usually, you know, if the width of the positive and the negative half wave is same, that means you have a 50% duty cycle. 50% of the time signal is going to be high, 50% of the time signal is going to be low. Looks like this looks like 75% of the time it is high and 25% of the time it is low, correct? So if you want to keep those duty cycles, say, like I said, you know, over here it looks like, oh, it says 63.89%. What it really means is 63.89% of time it's gonna be high, and the rest of the time, roughly about 36%, it's gonna be low. 36% is gonna be low, which is of not too much of significance for us, because our goal is to have a time delay of 1 second, and that's what we are striving for. So 63.89%, that's a duty cycle. In other words, like I was saying you earlier, if you convert that into like what amount of time it'll be high, it's basically 638.5 milliseconds, and amount of time when it's low, it's 360.9. and if you add these two values right here, you basically get this number right here. Okay, all right, so in case if you need to go with, say, a frequency of 2 hertz, right, you know, half a second, you can change these values and see what happens. If you say, if I change this to 60, and if I calculate, it goes to 0.9. If I make it 20 and then I make it 30 and I do it again, I get 1.8. I need to go to 2, right? 2 hertz. That would be 0.5 seconds, half a second. So say if I go with 32 and see what happens. Oh, I need to go to maybe 18. Calculate. Now 21. Let's see. So you see I'm getting to close to 2 hertz. And you just have to keep on doing, let's say 20.5. It's getting there. 21. 24 and so on. So it's pretty close to 2 hertz right now. If you can increase that number a little more, you'll get very close to 2 hertz. In fact, I got it 2 hertz right now. So the period is 500 milliseconds roughly, which is like half a second. If you want a time delay of half a second, then you want to go with the resistance value of R1, which is 20 kilo ohm, 26 kilo ohm for R2, capacitor 10 microfarad. In this configuration, if you create this circuit right here using R1, R2 and capacitor values as mentioned above, the output over here is going to give you a timing delay, whatever you see over here. Okay, few things over here. You can adjust the high time and low time. There are equations over here. This is for the high time, this is for the low time, and again, like I said, you know, it's not really critical for us because we only need a 1 second timing delay. Few notes over here. Increasing the capacitor value will increase the period, which means reduce the frequency because there's an inverse relationship between the two. Increasing R1 will increase high time without affecting the low time, and increasing R2 will increase the high time, will increase the low time, and decrease the duty cycle. Okay, so depending upon what application you may be working on, so say you want something to be on for a certain amount of time and then goes off. If that is critical, then you might want to change these values to adjust your high time and low time, right? Okay, this is pretty awesome. I love this article, so I thought I'll share it with you. And now we're gonna go to the circuit itself over here, and I'm gonna explain this circuit right here. So 555 timer, this is the ground simply connected over here. Okay, you have pin number 2, which is basically shorted with pin number 6 over here. If you go back here and if you look at the circuit, pin number 2 is just shorted with pin number 6, correct? Okay, let's look at pin number 3. Pin number 3 is the output. Pin number 3, if you look at pin number 3, is connected to this via this resistor to the positive terminal of the LED, and the negative terminal is connected to the ground, and hence you see this LED is basically blinking every 1 second. Okay, every 1 second it's blinking. But if you notice over here, the amount of time it's high, it's 63%. Remember we did that, the high time was 63%, and the time the LED is off is actually 38%. 63, let me go back actually. What were those numbers? We had 40 kilo ohm and 52 kilo ohm, right? 40 kilo ohm and 52 kilo ohm. So yeah, 638 milliseconds it's on, and 360 seconds it's millisecond it's off, right? So every 1 second it creates a trigger moment, and that trigger moment is fed into the clock of the counter, right? Pin number 4 is the this pin number 4 is basically the reset pin. So if you look at this circuit right here, pin number 4 is just hooked up to the terminal of R1 and VCC. Okay, so if you look at pin number 1 is hooked up to VCC, which is pin number 8, and it's connected to VCC. Let's look at pin number 5 is the control voltage. Remember, we are not using it. Pin number 6 is the threshold. Pin number 2 and pin number 6 were shorted, as I was showing you over here. 2 and 6 shorted. Pin number 6 is connected to R2, and the other terminal of the R2 is connected to R1, right? So if you look at it, this is my R1 vertical position and R2 vertical position. R1 here and R2 vertical position, just like I have on circuit. This node is connected to pin number 7. This yellow wire is connected to pin number 7. Then vertically we have a capacitor. So capacitor is connected to this R2, and the other end of the capacitor is connected to the ground, simply connected to the ground. And that's pretty much it. And like I said, you know, pin number 5, we're not using it here. They just connected to the ground via a small capacitor. If you wish to do that, you can also do that, but in you know, in this case it's just not simply going to. So 40 kilo ohms, again, these are not just random values. We did the math using calculator here. Well, the, you know, All About Circuits did the math for us. We just wanted to make sure that we get this value close to 1000, and which it is. So I'm just going, remember, getting a 50% duty cycle is going to be extremely difficult with a circuit like this. And also know that, you know, getting absolutely 1000 millisecond might not be too realistic, because resistors, they come in specific size. And since luckily we are doing this in a simulation environment, so we can pick these values, but if you don't have these exact value for the resistors, your timing delay might be little off. Okay, and then this is going to be 10 microfarad, not 47. So I'm gonna make that change here. 10 microfarad. Now what is next? Now we are going to look at this 74HC93, which is a 4-bit binary counter. This clock is fed into output bit 0. This is output bit 3. This is ground, so it's connected to the ground, and this pin is power, so it's connected to positive terminal, positive rail of the breadboard. You have output bit 1 and output bit 2. So these are the 4 output which are going to generate a binary code. All these 4 outputs through these green wires are hooked up to these 4 resistors. These 4 resistors, and these 4 resistors are running through these 4 LEDs. the anode of the 4 LEDs is connected to the resistor, and the cathode is basically connected to the ground via these black wires, right? We use the same output over here. We use the same outputs over here, all the outputs that you see over here in the green, and hook them up to 7-segment decoder. 7-segment decoder. Remember, 7-segment decoder will have pin number 3, which is a lamp test. That pin is going to be simply connected to the positive rail. Also, this pin number 4, which is the blanking pin, it's going to be connected to the positive rail. However, the latch enable is going to be connected to the negative rail of the power of your breadboard. This is your ground. This pin is your power. You connect those, and then you simply just make sure the output of the 74H9C93 becomes the input of the 7-segment decoder. Okay, over here at the output side you got segments. So say for example this is F segment, which is basically this wire. This wire is connected to segment F, right? Segment F. Similarly, if I look at this wire, this pin is pin number C, is hooked up to pin number C. This is pin number C. And similarly, I'm going to show you one more. This is G, and it's hooked up to G segment of the decoder. You have to make sure, folks, that this when you select this 7-segment decoder, it is set to cathode, and instead of having to connect resistor to each of the segment, you can just use a common, connect it to a 330 ohm resistor right here, and then connect it to the ground, and which will basically offer ground to all the LEDs within the 7-segment. Okay, now because I wanted this segment to start counting from 0 and goes up every 1 second, and once it reaches 15, obviously 15 makes a code of 1111, so 0 to 14 will basically make 15, and then it goes to 0 and then start counting back again. So I had to hook up the outputs to the AND gate. This is a 4-input AND gate. So when it reaches 15, which it does now, all the inputs are high. That means this is the input, the 4 input to C, to B, and to A. When all inputs are high, means it's 15. Again, it's 15 now. This logic goes 1, fed into the reset. The counter is reset, and therefore the counter goes to 0. And you saw that. And we'll see that one more time. 9, 10, 11, 12, 13, 14, 15 goes to 0. And lastly, if you just want to figure out if you have exactly a 1 second timer fed into the binary counter, we can actually match the number with the simulation number that's going to appear over here. Let's do that. Start simulation. 0, 1, 2, 3, 4. So the numbers are exactly matching, and that's because the values of these resistors were chosen such, and also the capacitor, that it's giving us a time delay very close to 1000 millisecond, which is equivalent to 1 second, right? And hence the two values are exact match. So 15 plus 5 is 20, so you get 20 here, right? I hope you enjoyed this video. This is very, very important. If you want me to, I can also share the link of my circuit, so at your leisure time you can also try build something. I could have build this circuit from the very scratch, but then it would have been a huge video and I wanted to keep it short. If you are very new to the Tinkercad environment, I have created a bunch of videos in the past. I will leave the link in the description as well. Also, if you haven't already, watch a couple of my last videos. They were based on Tinkercad. Enjoy your rest of the day, and if you haven't already, please subscribe to the channel. And lastly, I would like to thank all my patrons who have supported me in many ways, be it becoming a patron or liking and subscribing to my channel. Have a wonderful day. Bye.